Okay, so please welcome Matanya. Matanya is going to talk about algorithms in planning. Matanya is a software engineer in planning, and I'm very happy to host Matanya here in our Tech Talk. I already started the recording, and let's all enjoy the amazing talk that Matanya prepared for you. Matanya, the mic is yours.
Okay, thanks. Hi everyone, thanks for joining. So as we have said, in this session, I'll talk about some algorithms in our code, in the planning code, that feels to me like puzzles. But first of all, what is a puzzle? What the difference between a question to puzzles or riddle? For example, is this a puzzle or is this a question? If you ask, let's say, a math student, it says it's just a question because he knows how to solve two equations with two variables, and it's just follow the steps of solve it. But if you ask it 7, 8 years old child, it will definitely a puzzle because you need to think out of the box or to think not in a not ordinary way to solve this. And this is a famous puzzle, and you can also you can say, okay, it's a search problem in programming, but you also can treat it as a puzzle. It's not a question for programmers. It's a non-problem in the non-puzzle in the world. So as I said, me as a full-stack developer, sometimes I have many features like, okay, I need to add a dialog, add a file input, upload the file to the server, store it in the database, and so on. And sometimes I have, like in this session, I have several challenges that I need to think out of the box, and in all of the problems that I'll show here, there is not only one way to solve it. There are many ways to solve it. Okay, now I will not solve this puzzle, but if you want to think about several challenges in this session at home, so I have this home icon, so you can think about this at your home. Okay, let's start. Which algorithms I'm going to talk about? I'm going to talk about the sort trips, the combined route, the isochrone map, and the auto-add stores. Let's start with the sort trips. Here we can see our timetable. You can see this table. This is a table of trips. Each row is a trip. We have a trip that starts, the departure time is at 8 o'clock, and the second stop, it's 8 and 9 minutes. After this, 8 and 18 minutes, and so on. We have another trip that starts at 8 and 10 minutes, 8 and 19 minutes, and so on. And we can see that not all of the stops on all of the trips stops on all of the stops. This trip stops only on these 3 stops. This trip doesn't stop at this stop because we have many. You can have many routes, many patterns of routes, and so on. So the problem here is how to sort these trips. We want to sort trips by time, but it's not just sort by the departure time, because we can see that this trip started. This trip is at 8 and 10 minutes. It should be after the trip that started at 10. But if you look at this trip, he starts at 8 and 30 minutes, and this trip starts at 8 and 15 minutes. But if we will put this trip after this trip, what we will get? We have one indication of the sort. We have something that's called headway. You can see that. What is headway? Headway, it's in the departure stop of the trip. We can look at the previous trip at the same stop. So in this trip, it starts from here. It is 10 minutes after this trip. So we have headway of 10 minutes. This trip is 4 minutes after this stop. So we have headway of 4 minutes. So if we will put this strip after this strip, the headway will be a negative number. It will be minus 11 minutes. So this is one indication of a bad sorting. But something not so related in chess puzzles, in videos of chess puzzles, sometimes it's a common. In many times say, okay, now it's a good position to pause the video, and you can think about the problem. So now, if you see this video as recorded, or maybe if you have the ability to not to listen, and you want to think about this challenge yourself, now it's a good place to pause this video. I'll say several places in this session. So what is the problem? We want to how to sort all of these trips. Okay, now let's first let's take a step back and let's talk about sort in general. Okay, which sort algorithms do you know? Say open question, you can just throw names of
Bubble sort.
Bubble sort, excellent. Someone from the Zoom meeting, okay. Now you have many. Okay. Well,
Merge sort.
Yes, you get many names in the chat also. Yes, we have many bubble, selection, merge, heap sort. Okay. Now for a JavaScript developer. Okay, I have two questions here. First, which sort algorithm JavaScript uses? And the second, what will be the result of this line of code? Okay, somebody knows which sort algorithm JavaScript uses? I mean, it's not so important. It's a variation of quick sort. Okay, but what will be the result of this line? Do we have any JavaScript algorithm in the audience?
7, 25, 50.
Okay, this is I did this session for our team, and all the developers say that this will be the answer. 7 is the first, and they didn't believe me that this will be the answer. They even check during the session, they open the Chrome inspector and check that this will be the answer. Okay, but this is the answer. This is the answer that JavaScript default sort will return for this array. Well, why we get this strange sort? There are several like memes or sessions that jokes about the next fun of JavaScript. This can be one of these sessions. Yes, it's a what? Probably it's called the what session. There's something like what. Yes, but the default JavaScript sort is it's by string. So the 25, if you look at a string, it will be before 7. Okay, so how to fix it? If you want a rig sort by the number, how to fix it? Someone?
With the function there?
Yes, exactly. You can write a compare function. What's a compare function? What is compare function? We wrote a function that gets 2 items from the array that you want to sort, and this function returns a number. If it returns a positive number, it means that the first item should be after the second item. If it returns negative number, it means that the second item should be after the first item. And if it returns 0, it means that the two it's equals. We don't care about which stop will be first. So now you can see that the sort is okay. So let's go back to our timetable. So it sounds like that our our compare function should be something like, okay, you get 2 trips. We want to find the first common stop, and we compare the time at this stop. So if you get this strip and this strip, the first common stop is this stop, so we can compare 8 to 8 and 10 minutes, so we know that this strip should be after this strip. If you compare this strip to this strip, the first common stop is this, so you can see that 8 and 26 should be before 8 and 30. If you compare this strip to this strip, you can see that the first common stop is here, so 8:30 should be before 8:41. Okay, what happens if we compare these 2 trips? They have no common stop. Let's focus on this problem. Okay, now this is the problem that I talk about. Now we have 2 trips. We have trips that stop at the first and second stop at 8 and 9. You have another trips that stop at 10 and 11. They don't have any common stop. So which strip should be first. If you have only these two trips, you don't know which trip should be first. Let's say you have three trips. You have these two trips and another trip. You have another trip that stops at all of the stops. It stops at 8:30, 9:30, 9:31, 10:31. So now you can see that this trip should be after this trip because it's 8:30 and this is 8. And this trip should be after this trip. So because 8 is after 9:31, so definitely this should be after this. But if in other case, if we have these three trips, we have our two trips that we know from the beginning, but this is the third trip. So now this trip should be after this, and this should be after this. So definitely this should be this. So as I said before, we have in all of our in most of the sort functions that we know, like bubble sort, selection sort, merge sort, we have two items, and let's say the bubble sort, it knows which item to bubble if it's bigger or smaller. But all of this sort don't know how to handle this new case. We have also the unknown case. We don't have only bigger, smaller, and equals. Now we have now a more generic problem. It's also a good place to pause the video if you want to think how can we sort items. Now it's even general problem. It's not. I'm not talking about trips and so on. We have this 3 or 4 new these 3 or 4 options of the compare. That one of the options is unknown. So if someone knows the answer, probably I know someone knows this is a known problem that even I took the next slide from Wikipedia. So it's something that's called topological sort. So like in many, the solution to many interview questions for programmers is start with let's draw a graph. So here we draw a graph of our items, and we draw arrows, we draw edges, which should be before which node should be before which node. So we know that 3 should be before 8. But we don't know that 3 should be before 9. It's according to other arrows, we don't know it immediately, but our sort should do this. So there's not only one answer. You can see here many solutions to this sort, and this is something from Wikipedia. But this is exactly, I just implement this code in our the functions that sort the trips. Okay, so let's look at this code. We have L. L will be the output of this function. It's a list of the sorted elements. It starts with empty list. And this algorithm will fill it with the items. And we have S. What is S? S, it's all the nodes without incoming error, without incoming edges. So it starts. Let's do this. We have the 5, 7, and 3. This is the S at the beginning. Until it's not empty. We remove a node from S. Let's remove 5. Now we go for each edge, for each node with an edge E from N to M. We go on all the arrows that start from this node. We have only this arrow, so we delete this arrow, and now we check if this new node has no other incoming edges. It's not our case because we have this edge. So we finish. Now we go to the next item. So in 7, we delete this arrow, and 11. Now it has no more incoming nodes. So we add the 11 to our S, to our set that we are loop on it. And now we delete this arrow, but 8 has another arrow, so we don't insert it into S. Now because we insert 11, so now we go on 11. We delete this arrow. We insert 2 to our S. We delete this arrow. We don't insert because there's another arrow. And so you can see that this is the answer we'll get. We get 7, 5, 11. After this, we go on 3. We'll delete this, so we get 3. After this, we get that. So this will be our answer. Sorry. First, all of these possible options. If you insert this node to the end of the set or at the beginning and so on, but this will be in what I show here. We get this. We start with 5, 7, 11. After this, we have the 2. After this, we go to 3, 8, and so on. Okay, we have any questions? Let's say 1 minute. If not, it's good. Yeah, maybe I'll get more. Okay, now another puzzle or another algorithm. We see the same view that we saw before. Now I'm talking about what we call combined route. What is combined route? Let's say that in this view we want to see several routes, and each route stops on its stop. We have a route that's called train, and the train stop in Tel Aviv, train station Tel Aviv, and train station Netanya. We have a route that's called detour that stop at train station Netanya, Rabbi Akiva or something, Merkaz David. We have 613 that stops at train station Netanya, Derech Dgania, and train station Tel Aviv. So what is the problem? What we want to do? We want to calculate this list of stops, and this list of stops should come. All of our routes that in this view should be subset of this list of stops, and we want to merge as many stops as we can. So you can see that here the train station Netanya appears also in this route, and in this also we use the same stop here for both of them, and you can see that train station Tel Aviv appears twice. It appears also here and also here. Why it appears twice? Because this route stop in this stop, but also in this stop, and this route also stop in this stop and in this stop. But I can't use, if I combine, I can combine the 5, the train station Tel Aviv here, but I can't combine this one. So let's talk about, let's see that you understand exactly the problem. So let's say you have only.
Yeah, maybe I want to say a few words about the use case. So think of a corridor where many routes go to the same stops, and now the user wants to plan the trips of all these routes in one view. So how can we see the sequence of stops, and how can we basically combine them in a way that makes the most sense, where we're not having the same stop twice?
Yes.
I have examples of places in Tel Aviv, but I don't know how many people know Even Gvirol or
Yes.
but probably anyone can think about the main street where many buses go through, and then they deviate to different places.
Yes, as I would say, before I said that you want to combine as many stops as you can. So why you want to combine the routes? There are several reasons. One reason is just, Oren said, the user wants to see the trips that go at the same stop. He doesn't want to scroll and to find if this stop appears in more places. And there are other reasons, like performance. If you have table with 200 columns, it will be also in the bad performance. So we want to combine the stops. So let's as I said before, let's say that we understand what will be the good solutions. Let's say that we have only 2 routes, one stop at A, B, C, and one stop at B, A. So we have four solutions. So if you need to score each solution, what do you say about, let's say about the first solution? Is it a good one? Let's say score it between 0 to 10 or something. Okay, I think the first one is good. What do you say about the second one? Okay, I think they are both a good solution because it's the most shortest. No, there are no shortest, so probably it's a good solution. What about this? It's not so good because you duplicate the A stop. You can combine, but you didn't combine it, and we didn't combine even the B. So it's a valid solution, but it's not a good solution. What do you say about the last one? The last one is not a valid solution at all because this route of BA is not subset of this combined route. We have both B and we have both A, but the order is matter. So we don't have a B that comes before A. We have B that comes only after A. Okay. So now again, it's a good place to pause the video and to think about this problem. Okay. In the beginning, what was our? We developed a solution to this problem, and it's not an easy problem. we use algorithms called longest common subsequence. It's again, it's a famous algorithm. For example, you can see if you compare versions of, let's say, in Git or something, we find the longest common subsequence. So you can see in these two sentences, this is and change, it's the longest common subsequence. Okay, so it stays the same in these two sentences, or in our case, in two routes. And this problem, it's what called in computer NP-hard problem, which means that if we are using a big input, so this problems will not. The science today doesn't know how to solve it in a reasonable time, so we take ages to solve a big problem. So this is what in the beginning we use the longest common sequence, and we also use it recursively, because after we merge two stops, we run it again for all the stops between the subsequence, and we also run it not just on two routes. We can run it on 5 routes and so on. So we have very bad performance. So the algorithm took some lots of time. So we did several things. First, we restrict the number of routes and stops that you can use our combined route. And after this, because our users need to see the combined route, so we also run it on what we call time points. We have two types of stops on route. We have time point and bus stop. Let's say it's important stop and unimportant stop. So we run it only on time points. So let's say you have these two routes. The pink color is time point and the blue color is bus stop. So we have now you can see it's like a problem that now I look at it. I don't know what will be the perfect solution for all of the stops, because if I combine this B with this B, I can combine this A with this A and so on. So it's hard to solve this. So, and we use, as I say, because we run it only on time points, what will be the result? We run our algorithm on AA in route 1 and AC in route 2, and the solution of our algorithm will be AAC. This is the solution, and we copy all of the sequence between the time point. We copy it again, so we get this huge list of stops between these two stops of route 1 we have in the combined route, and also this huge list of stops from route 2, it's here. Okay, but the routes in the world doesn't look, I don't know if a real route stops at stop A, B, C, B, A, D, B, D, B, and so on. Routes are not going in this strange way. So maybe it's theoretical, but if in every like real world problems that we look, it sounds like something like this. We have this, let's say we have this 3 routes, okay? What will be our solution, as we said before? Because we look only on time point, so we say, okay, the combined route will be A, E, J, N, and Z. So we took the B, C, D from here, we duplicate it, A, B, C, D, and now we took also the B, C, D, E, F, G, H, and again we have A, B, C, D, B, C, D, E, F, G, H, and we have again B, C, D, again here B, C, D, and after this we have the E. And now we duplicate all of this one, F, G, H, I, J, G, H, I, it's this and this, and after this we have between J to N, we have K, L, M twice, and so on. So it's not a good solution, because now if you look at the timetable, you can see the corridor as Oren said before, and you get a big timetable that can cause the performance even during working on the timetable, because you can have many columns. But if I look at this one, this happens every time. When you look as a human, you don't need to calculate very hard problems. You say, okay, what will be the good solutions? It's very easy to see. You can say, okay, I can combine A, B, C, D, E, F, G, H, now I, J, K, now we have here it's at X and here it's L. So let's say one will be X, Y, Z, and after this L, M, N, or the other side. So it's look like very easy solution. So it's every time that you look at it, in 1 second you can say, okay, this should be the combined route. No, it just says that what was the trigger that, for you to change it. We had one time we had a bug. That's we get there was an exception in our code, so we have a case of 6 route combined route of 6 routes with each route contains dozens of stops. So our solution returns hundreds of stops, but there was a problem because we get a JavaScript exception something inside it, but it took me because the code is very, very complicated. It's a longest common subsequence. It's a very common, very complex algorithm, and we run it recursively, and we run it on several. So it took me something like 2 or 3 days to solve the bug, and also the result was very bad because we got combined route of okay. We got combined route of hundreds of stops, and it reminds me this joke. What is noisy? Smoke making, and cuts apples into 3 pieces. So it's a Soviet machine that cuts apple into quarters. Because we have an algorithm that took the performance of running the algorithm took many time, and there was bug in it, and even after it does everything, the result is so bad that you can look and say, why you duplicate this corridor of these 6 routes again and again and again. You get the same corridor 6 times every time because the corridor contains many bus stops, so we get a bad result. Okay. Again, let's take a step back. As I said in one of the previous slides, it is really a complicated problem, but you sometimes have complicated problems. For example, where there is a very famous problem called the traveling salesman problem. By the way, I think here in Optibus we really love this problem. Even in the last hackathon, we have 2 groups that did products that.
I think every hackathon there's at least 2 groups that do it. Yeah. So okay, well, again, this problem is also a NP-hard or NP-complete problem that you can't solve it, because if you check what is this, let's say, what is the problem, you have several places or stops, and you want to, and you know the distances or the time between all of the stops, and you want to find the shortest route if you want to go on all of the stops. So this one is not a good solution because it's not the shortest, but this one is the shortest, so it's good. But if you can easily write a code that check all of the combined routes, but all of the combined routes, it's factorial of n. Again, it's a very, maybe it will work for 7 stops, but if you have 70 stops, it will take a zillion years or something like this. So how to, okay, so how do we do it? So something, okay, you can say something, okay, we are not committed to the best optimal solution, but let's do something good enough. For example, if I want to solve it, I will not check all of the combined, all of the possible routes. I'm just, let's say I want every time I want to go to the first stop, it's the closest stop. So if I start from here, I'll go, this is the closest stop, this is one, the closest, is the closest, so we get this solution. Maybe sometimes you will not get the, let's say something, you do something like this, maybe it's not in this optimal solution, so we have a little place. Maybe you can say something, okay, from one hand, we will not check all of the combined, all of the potential stops. We check, and from that one, you say, okay, you could say, okay, let's check one stop. Maybe say, let's find the 2 or 3 closest stop and so on. So this is what I say. Okay, I can use something very simple. I'm not guarantee, I'm not committed to the best solution, but in all of our cases, even today, that we use it for, I think, something like 2 years, I never see a case that it didn't return the best solution. And now, when we use this algorithm, I can, because it's very quick, I can use it on all of the stops. I don't care if it's a bus stop, tire point, and so on. So I can combine all of this. So what was the simple algorithm? It's not so complicated. I just, let's say I want to combine the 6 routes. Every time I combine one route to our combined route.
and I use two indexes. On two routes I want to combine. I have two indexes, and every time I search for this A, it doesn't come here. I go to the next one. B doesn't appear here. C doesn't appear here. D doesn't appear here. E. Now I found this E1. So now this is our first step. Will be combined stop, and now I need to copy all of the stops from this index to the stop, and from this index to the stop. So now I copy the A, B, C, D, and 1, 2, 3. Sometimes we can give some hints if we want that this sequence should be before the sequence, before this sequence or after this sequence. For example, if D and 1, it's the same stop, they have the same place, but it's not the same stop exactly, but they have the same place or maybe the same hub, so we can decide to put it together, but it's not so important now. Again, now we continue. F appears also here, F and F. G also here. H, now H appears here, now I go until J. J appears here, so I copy. Again, I can decide if to put I before X or on the other side. After this K, and after this I get to the end, and now again I copy the both remaining sequence, and this will be our solution. Now again, you can think about two things. First, as I said before, like in our greedy algorithm, what will be which case of like real world case that this algorithm will not return the optimal solution. And by the way, I thought about it in the beginning, but I said, okay, let's start from this simple one, and after this I will add something like in the example of the traveling salesman. I say something like, okay, now I can check two stops. So one is in which case this algorithm will not return the optimal solution. I mean, not just giving a sequence of A, B, C, D, A, B, A, B, C, about like a real routes, and how can we fix it? Okay, again, you can think about it from. Okay, now again, solution, questions? Okay.
Yeah.
Yes.
I just have a question. Like did we or you ever think like this is like solving it in like as like a string problem? Did we ever try to look at it as a quarter with like or getting hints?
Can you repeat? I didn't hear you well.
I think it was twice, and one is okay. Can you hear me?
Yes.
Okay. Did we ever think about solving it also with like location, right? Because it's in the end, it's not only like a string problem. Like the quarter problem is like if it goes to even the roll, we can maybe like do it with like matching of like locations or paths or something.
Okay, it's an interesting idea. Yes, as I said in the beginning, there can be many solutions to this puzzle. Again, it can be a good solution, a good way to think. Maybe to combine the stops with the geolocation and so on. But I think that, as I said before, when we use this algorithm, we didn't see cases that our customers will say something like, why do you combine this? I want a different solution, different combined route. So if I assume that if you have some cases like this, I don't know, if you reach cases that maybe you can think, okay, now you can think about a different algorithm that solve this problem with using the geolocation of the stops. But as I said before, we never need it.
Cool. It's probably even harder to do it with the location, I guess.
Yes. Okay. And now to the next algorithm. We have the isochron map. So what is the isochron map? So we have our network of many routes, many trips, we know the times of the trips and so on. And we have also all of the stops catalog. We have the entire, what we call time plane. We have the entire network of public transportation. And our user want to see something like they want to pin a place on the map, let's say here. and they want to see if there is a passenger that starts from here, let's say at 10 o'clock, and we have several restrictions. For example, you can change trips and change routes only twice, you can walk only 5 minutes walk maximum and so on. So how many times it will take him to be in different places in the city, which places will take him 15 minutes. For example, it starts from here, it can be in this circle in 15 minutes. It can be here in 20 minutes. It can be here in, 45 minutes. It can be here at 20 minutes. It can be here until 1 hour, until 60. So this is what we want to see. And another example of this one, it's now I just change the several parameters. I change the position, also change it from to to. I can ask the opposite question. So I want to come to this place at 10 o'clock. How many times it will take me to come from places in the city to this position? And now I also change the maximum walking time or distance from 5 minutes to bigger. So now we don't get this many small circles. Now we have more racif, more. Never mind. We get this. So how can we run the algorithms that will calculate this isochron? Okay, we inspired of even more. There's the algorithm called the Dijkstra. That is, it sounds nearly our problem. So what is this algorithm? If you have graph with edges and all of the edges have positive and not negative number. So if you have negative number, for example, in our case, if you can go back in time, it will not work. But it's not our case. So this algorithm talk about how can, if you start from one edge, from one node, what is the shortest path to a specific node or to all of the nodes? So Sababa. Okay, so in this algorithm, it's something like, okay, you start all of the nodes with an infinity number, and every time that if you go to a node with a number, if you are going to with the sum of the number to this node is smaller, you can update this node with this new number, and you remove it from the done set of nodes. So let's look at our algorithm. First of all, at the beginning, I index all of the trip segments. So if you have trips that stops at start at 10 o'clock at stop A, and you go to stop B, after this to stop C, after this to stop D, I index all of the segments of the trips at the time, and also I index with the geolocation, geo-index, all of the stops for walking. I do it so every time if I want to know how many time it will take me to go by trip or by walking from stop A to stop B, I will get it immediately. After I finish with this indexing, I have a queue of, it's like the queue here, it's a queue of like in progress position. So I start with the start positions that we get, that the user choose. And now, while queue isn't empty, in the beginning it will include only one place, which is the start position. I remove this one stop from this queue, and now I'm start from this stop. I'm checking on which stop from this stop S can get by walking too many stops for. With all of the restriction, I have only, let's say I have only 5 minutes. This is what parameters that the user choose only to walk maximum 5 minutes, or maybe I have only 1 hour of the entire isochron. It's only maximum 1 hour. So if I'm at if I start at 10 o'clock and now it's 9:58, I have only 2 minutes of walking. So I add stops by walking, and every time that I want to add stops by walking, I'm checking if I'm let's say that now I in stop S I have after 20 minutes, and now I can walk 3 minutes and be in after 22 minutes at stop X. So if at X we have infinity or something, I'm adding it. But if it had something like a 10 minutes, so I don't use it because I have another path to go to the stop. So I'm adding it only if it's a smaller time. So I first start stop from S by walking. After this, I add stops by using a trip, and after this, I mark S as done. Now I'm continuing until Q is empty. But at the end, now I have many done stops of and in each time, let's say in stop A, it took me 10 minutes. In stop B, it took me 20 minutes, and so on. After this, I can convert, I can create a polygon or a circle around each stop of walking from this stop to the edges to the border of how many this passenger can travel. And now I have this layer of polygon. So let's look at the example. Now let's say I start here. It's 0 minutes because I only start. This is our queue of in progress position. Start with the start position. And now, let's say by walking, it took me 5 minutes to here, 12 minutes to here, 10 minutes to here. And now I added these 3 stops to our queue in progress. Now, by trips, I will not get any result here because this is not a stop. I'll just start from a position on the sidewalk or in the building. Okay, now I finish with A, with the start position, and now in this example, I'll start with B. In our algorithm, I'll start with the closest, I'll start with A, but now to demonstrate for the demo, let's start now, in the queue, let's work from B. Okay, let's say that we have 10 minutes by walking to here, so we ignore this because 12 plus 10, it's bigger than 5, so we don't use this, and we don't use this, and now we get, let's say, also 10 here, so we added D to the queue, and we also added the 22 minutes to D. Okay, now we finish, we remove this B from here, and B go to here. Now we are looking at C. Let's say, again, this is not good enough, we ignore it, this is not good enough. This is, I think there was a little animation, now, okay, now it was 10 minutes, so I changed the time of D to be 20 minutes. Okay, now we finish with C. Now we are in A. Again, we change the B, the time of B. So if you can see that now it's B is come back to the queue because I changed it. Although I already checked it, but now I need to check it again because now it will work with only 11 minutes. Okay, now I'm working on D. Let's say D doesn't add anything because it's not good enough. Now we go again to B. Now, again, let's say this B will not add anything. Maybe if this B will get a shorter time to D, I need to, again, to update D and insert D to the queue. So after I finish everything, now the queue is empty. Now I convert we have all of this, we have this 5 position. I can draw a circles with walking. So this will be our isochron result. Okay, now two things that you can think about at home. Okay, now we show how to handle from. We start from a position, and we want to see all of the places that I can reach. How do we handle the opposite case? That we have a position, and we want to find all of the places that will reach to this position. This is one pretty simple. And another thing, now we handle a specific time. It says, okay, I start at 10 o'clock or at 5 o'clock, the user will answer the time, specific time. How do you handle time range? Let's say that the user I want to see the isochron between 7 to 10. Now it's not just how to calculate, it's even includes many product questions. For example, how if you can treat between 10 to 8, what happens if you come in 8, it will take you 20 minutes. If you go with 9, it will take you 25 minutes. If you go in the 9 and 7 minutes, you will never reach because there are no trips and so on. So there are several product questions also about what we want to handle in time range because it's not so clear what the product is. Okay. Any questions? Okay, now to our last thing. So I didn't know if I have time, so I'll just this will be only I think about at home because I didn't think that I will finish the time. So what is the problem? Auto-add stops. Let's say that we have shape of a route. We know this shape, and we also have the stops catalog. We know a position of many stops. We can see all of the circles here. There are many stops that we have in the stops catalog. Now the user wants to auto-add stops to this shape. You can see, okay, I want stop every 1.5 mile, or maybe every 20 meters, and so on. And now this action will add a stop. Now you can see this orange part of the stops became orange. And another problem here, it's not just adding a stop with this delta, with minimum delta that I asked before. There was another problem. Let's say that in this shape, in this code, there are two stops on the two sides of the road. And let's say in Israel, we drive on the right side. So if we go here, we don't want to add the stops at the other side of the road because the bus will not stop there. So the problem here is how to add the stops, but only on the right side of the road, right or left if it's in English or something. So again, you can think about it at home. Okay, that's all. So, any question or something? Thanks.
Thank you very much, Matania. Do anyone have questions for Matania before we end up the session?
Okay.
Amazing. So thank you all for joining us. Thank you, Matania, for preparing the session. And see you next time. Thank you all.
Yeah.
Bye.
המנחה שלנו.